In this video, we are going to look at Rutherford's gold foil experiment and how important this was for him to explain a new concept of what the atom looked like. Now, one of my favorite quotes of Ernest Rutherford was, "All science is either physics or just stamp collecting." So here is his experiment. So right here, in this little particle emitter, he had radium. And he found out that radium decays and emits something called alpha particles, which is a lot bigger. He knew the mass of it was bigger than electrons. So the alpha particles would be ejected from the radium through this slit of our detecting screen, which is going to be a zinc sulfide screen, and it would hit or go through this thin gold foil. Now, what he would expect is, because remember we had this raisin bun model, is all of the alpha particles would mostly go straight through or slightly get deflected from the charges of the alpha particle, which is going to be positively charged, and the electrons, which are going to be negatively charged, are going to deflect it in certain ways. Just the charges will deflect it. But something weird happened. He also noticed on his detecting screen that some shot right back, like that. Some alpha particles didn't just deflect, but they rebounded. This was completely unexpected. Rutherford knew that an alpha particle was a lot bigger and heavier than an electron, and it was coming here at quite a bit of pace. And yet these electrons are just staying there. Let's just think of simple momentum here. How would it ever shoot back or reflect back? Yes, it makes sense that the charges of them would deflect them out that way. So according to J.J. Thomson's model, they should not reflect back, but because there's just these sponges, or you might say the raisin bun model, raisins of electrons in a bigger sponge. So why are they reflecting back? When Rutherford observed his results, he said that having the alpha particle bounce off the foil was equivalent to seeing a cannonball bouncing off a piece of tissue paper. This should not happen. So then there must have been something wrong with Thomson's model. And therefore, Rutherford came up with the planetary model of an atom. It was one of the first significant attempts to describe the atom as chemists know it today. The model describes the atom as being a small volume nucleus that concentrates the vast majority of the atom's mass. At a considerable distance from the nucleus, the electrons are orbiting in spaces of nothingness. So let's think about it this way. Remember in grade 9 we watched that video with a blueberry in the middle of a football stadium. The blueberry, he said, is the nucleus. And every once in a while, this alpha particle would hit the nucleus, which is the whole mass, and then bounce off. And that is why this is happening. This created something very revolutionary. Now I want you guys to think about this and explain how the results from Rutherford's gold foil experiment disproved Thomson's model of the atom. I also want you to think of why does the scattering angle increase as the alpha particle passes closer to the nucleus. I want you to think of what you know about the nucleus. And here's a little hint about the alpha particle. It is a positive, pretty much helium particle. It's just another word, it's an alpha particle. So now why would, as it gets closer to the nucleus, be deflected more or eventually just reflect? So Rutherford's model wasn't perfect. There were some flaws in it. And then along came a scientist named Niels Bohr, who really focused on his negatives. So here's a little interesting tad bit about Niels Bohr. So he would often close his public speeches with humorous stories to further drive home his point. One of them was, one of our neighbors in Tisville once fixed horseshoes over the door of his house. When a common friend asked him, "But are you really superstitious? Do you honestly believe this horseshoe will bring you luck?" He replied, "Of course not, but they say it works even if you don't believe in it." So, obviously, there was flaws in these planetary model. So here's the first flaw. The negative charges should spiral into the nucleus. After all, positive and negatives attract. Another flaw was this. The electrons are traveling in circles, therefore they are accelerating. All accelerating charges create what? Well, they create electromagnetic radiation. So looking at that there, this leaves another big question. As this electron's accelerating, it should be losing electromagnetic radiation, which is losing energy, causing it to further go into my nucleus and eventually crash into the nucleus. This should be the death of the electron crashing into the nucleus. But it does not. Why does this not happen? Well, Bohr would start looking at something called spectroscopy. So first of all, what is spectroscopy? Well, spectroscopy is the study of light emitted and absorbed by different materials. Now, why would Bohr be looking at that and be curious about that? Well, it has to do first with, in 1814, Joseph von Fraunhofer, who noticed a number of gaps in the lines of the spectrum of the sun. Then later, a German physicist named Gustav Kirchhoff had established that gases and elements of compounds under low pressure each have a unique spectrum. So Kirchhoff and others used this spectra to identify the unknown elements in our periodic table. So Kirchhoff's laws for spectra explain how temperature and pressure affect the light or absorption by a material. Now, why is this so important? Well, let's first go over some more interesting things about spectroscopy. So first of all, if we have a high, hot, dense light without any dark or bright lines, it's called a continuous spectrum. That's like white light. White light will make this continuous spectrum. Now, if we have a hot gas at low pressure, it creates something called an emission line spectrum. So it is emitting certain things here. So certain colors or wavelengths are being emitted. Because remember, we know light is electromagnetic radiation. So they're emitting only certain wavelengths, which is kind of interesting. And every element, you might say, has its own signature, unique signature. And then last, we have something called an absorption spectrum. So an absorption spectrum is a gas at low pressure and a cold gas. And when it's heated, it absorbs certain light or certain wavelengths from the wavelength spectrum. So it absorbs certain light or wavelengths from our continuous spectrum. So here's an example of radium. So once again, absorption lines are dark pattern lines, and we have emission lines are bright spots in dark lines, so colors coming on dark lines. How do you do this? Well, he used a prism and gas with a prism to figure out which lines were shot out by the spectrum. Now let's look more closely at how they found these spectrums for different elements. So first of all, let's look at white light. So we have a bright white light, and it's shining through a prism, and we know that this prism will refract the light. So eventually, we see all the colors of the white light like this. Now, a hot gas emits electromagnetic radiation as well. And it will refract everything, so we end up seeing only certain wavelengths of light after it's refracted through a prism. Then, we are going to have a cold gas. We're going to shine white light through a cold gas. Now, something interesting happens here. Here, we have black lines through our light spectrum. So that must mean this is absorbed. These lines are absorbed by the gas and not emitted. And then once it's heated, it emits these lines over here, which is my emission spectrum. So these lines will match up with each other right there. So once it's heated, then it will emit these. Now, why is this so important? Well, if we remember, with an electron moving, it will create electromagnetic radiation. So Bohr would use the emission spectrum and spectroscopy to help build on Rutherford's model, or correct Rutherford's model, of the atom. And we're going to learn about that more in the next video.